Thank you for watching today's episode. Before we begin, I'd like to share just a little bit about myself. My name is Henry Skirpst, but you can call me Mr. S today, and the S stands for science. I have been a science teacher for almost the last 30 years of my life. And throughout that time, and even before, there are a few things that interest me most. I have always had a fascination for science. Everything science I love. I love learning about science, and I love sharing that knowledge with others. The second thing that I've always enjoyed is our great state of New Jersey. Being born and raised in New Jersey, I have become in love with the people, the places, and the past of our great state. From the mountains to the shore, from the cities to the country, and everything in between, New Jersey is a fantastic state with such diversity and variety packed into such a small area. The third thing that I've always enjoyed is PBS. Some of my favorite shows as a kid are still my favorite shows today. I look forward to watching Nova all the time and the wonderful science that they present in such a marvelous way. So again, I thank you for watching today's episode, and I hope you enjoy it. Now I have to warn you, today's episode is only for scientists. No, wait, don't leave. Don't leave. You might be asking yourself, am I a scientist? Wait, I can't watch it if I'm not a scientist. Well, let's find out if you're a scientist or not, shall we? There are 3 requirements for being a scientist. Number 1, you must be curious. Are you curious? Are you curious about anything? Number 2, the second requirement, you ask questions. Have you ever asked questions? And requirement number 3, you want answers to those questions. Have you ever wanted answers to the questions you ask because you're curious? If so, you are a scientist, and I invite you now to join me on this adventure of discovery as we have a science lesson on a topic that holds the whole universe together. That topic is gravity. Oh, hello there! Sorry, I didn't see you watching me as I was practicing the violin. I want you to think about what I was just doing. What was I doing with the bow in order to make, well, what some people could call music? What am I doing to the bow? Think about that for a moment. Hey, my name is the element of surprise. And I'm going to be asking Mr. S some questions during his lesson. Yeah, what makes something move? Well, I think we can answer that question with one word. And that word is force. A force is a push or a pull on an object. Now, there are different kinds of forces, but when forces are in opposite directions and they're equal, there's no motion. But if one force is greater than the other, then watch and see what happens. In this experiment, we are going to demonstrate what happens when there are unbalanced forces. I, as the scientist, have challenged my daughter Kayla to an arm wrestling competition. Kayla, are you ready?
Yes.
Take notice of her bulging biceps. Now, Kayla will be applying a force in a direction away from the camera, and I am going to be applying a force toward the camera. Right now, we are both in a balanced state. We're both applying the same force in opposite directions. But when I say go, let's notice what happens when there is an unbalanced force. Are you ready?
Yes.
Get set. Go. Ah! Wow. There was an unbalanced force. Her force was greater than mine, and that resulted in a movement of our arms away from the camera. You'll have to excuse me now because I think I need to see a doctor for a dislocated shoulder. Thank you, Kayla, for your help. When will the ball move? So how long do you think it will take? Never? Why? Oh, I have to either push or pull the ball to get it moving, right? A push or pull on something. What do we call that? That's right, a force. In order for an object to move, you have to apply a force, either pushing or pulling an object. But in nature, objects tend to be at rest. Everything wants to be at rest. And there's a word for this. It's called inertia. Inertia is a property of matter that all things have, all things possess, and the word inertia is actually Latin, and it means lazy. How many of you have ever been lazy? Well, let's check out this next clip dealing with inertia and laziness. Kendall, time to get up. Kendall, time to get out of bed. Inertia Man will save the day.
I'm up. I'm up.
How can you make that go faster? Now that we know that all objects have inertia or laziness, and in order to move objects, we have to apply a force, this question can actually be answered with an equation. And that equation is F equals ma. Now don't be scared. If this looks foreign to you, that's okay. Let me read it to you. It is an equation that says force is equal to mass times acceleration. So what does this mean? Well, if you want to get something to go faster, fast is a measure of acceleration, A. What do you think you're going to have to do to get something to go faster? That's right. You're going to have to either push it or pull it harder. That pushing or pulling is a force. So there's a relationship here between force and acceleration. The m for mass is how heavy something is. So let's check out this relationship between how fast something goes and how much force is required to accomplish that.
We are on location to do our next experiment. My faithful assistant, my daughter Kayla, who's currently in the red wagon, is going to be my volunteer. I am going to apply forces to the wagon. I'm going to first pull the wagon, and then I'm going to push the wagon. I'm going to be applying these forces, and I want you to watch and see what happens. So let's begin with the first one, a small, gentle pull. La, 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 la. Gentle pull. Next, a hard pull. Now, a soft push. And now, finally, a hard push.
Whoa! Oof! What causes a rocket to fly up? Well, rockets are cool, and rockets travel far into space. I'd love to be on a rocket someday, but the basic answer to this question is two words. Action, reaction. For every action, there is an equal and opposite reaction. For example, if someone were to throw a ball to me, that would be an action. My reaction would be to catch that ball. Likewise, my action could be to throw the ball to someone else, and the reaction would be the same. To respond, to catch it or drop it as the case may be. But that would be an example of an action-reaction. But there are some other examples as well. Maybe you've seen one of these before. They're loads of fun to play with. You can take one of these steel marbles up and let it go. Watch what happens. Ooh, yeah, very cool. It's mesmerizing. You could watch it for a long time. You take two of them up and let two of them go. Watch this. Wow, how cool is that? You can do all sorts of really interesting things with this device, which is called, do you know what it's called? That's right, it's a Newton's cradle. There's interesting experiments you can do with a Newton's cradle, but it's named after a very famous scientist, Sir Isaac Newton. And what we have just done is gone through three of his laws of motion. Isaac Newton's three laws of motion are as follows. His first law is inertia. Do you remember what inertia also means? That's right, lazy. His second law of motion is an equation, F equals ma, or force equals mass times acceleration. And do you remember what you have to do to accelerate or make something go faster? That's right, apply a harder force. Very good. And his third law of motion is action-reaction. For every action, there's an equal and opposite reaction, and that's what our first activity is all about. This is one of my favorite activities, and it's also one of the simplest. We just learned about Newton's three laws of motion. Do you remember what Newton's third law of motion was? Action, reaction. And that's the law that helps to explain why rocket ships fly up. So we're going to make a little rocket ship out of some simple materials. You may even have them at home. And what I'm talking about are straws. Be honest with me, do any of you love playing with straws? I'm sure you do. So let me show you a quick little activity here that illustrates Newton's third law of motion. We're going to make a straw wrapper rocket. And here's how we do it. Simply take a straw and remove only one end of the wrapper. Just one end. Don't tear it all the way off. Just one end so that the straw slides back and forth. Now, don't take the straw all the way out yet. Don't do that. But on the opposite end, the end that you didn't open, curl it down and crumple it together a little bit. What that does is increase the center of mass forward. Gives it a little bit more weight in the front, if you know what I mean. So if you roll it up into a little ball, really nicely and very carefully so you don't tear the wrapper, now your soda straw wrapper rocket is ready to fly. Now before I show you, you have to promise me. Put your right hand up and say, I promise not to shoot my rocket at anybody else. I promise. All right, so now that you've promised not to shoot your wrapper at anybody else, here's how the rocket is launched. You put the straw carefully in your mouth on the opened end, and you aim it away from other people, and you take a deep breath. And as you take a deep breath, you put your lips on the straw, and then you exhale or breathe out very quickly. Are you ready? Whoa, that was probably so fast you didn't even see it. So let me make another one for you. Again, we take a soda straw, open up one side of the wrapper so the straw slides in and out, but don't take it all the way out. Crumple up the opposite end of the wrapper to increase the center of mass there. Put your mouth on it, take a breath, and let it fly. Are you ready? Here it goes. Hopefully you got to see it that time. Now, I'm going to make another one because I want to explain one more thing to you. So again, we remove the wrapper from one end, loosen up the straw, and crumple up the opposite end of the wrapper. Because here's what's happening from a scientist's perspective. Why does the wrapper fly off like a rocket? Well, when you blow air into the straw, you are filling the wrapper with air. And that air has to go somewhere, and it can't go back down your mouth. And so what happens is, when that wrapper fills with air, the air shoots out the end of the wrapper. There's your action. And the opposite and equal reaction is your rocket flying in the opposite direction. So Newton's third law of motion, action, reaction. Have fun with your rocket. What will happen if I drop this ball from my hand? Think about it. Did you say it'll fall? You want to see it again? What will happen if I drop the ball? You're right. It fell. What happens after you jump up? I think we know the answer to that question, but why don't you give it a try? Take a moment right now, stand up, stretch your arms a little bit, and on the count of 3, jump as high as you can. Are you ready? 1, 2, 3. Now don't come down until I ask you to. Whoa, wait a minute. I said don't come down yet. No. Let's try that again. Let's try it again. This time I'm going to count to 3. You're going to jump as high as you can, but don't come down yet. So let's try it one more time. 1, 2, 3. Why did you come down again? Oh, did I hear you say this word? Gravity. That's right. Now, we all know about gravity. It's what keeps us on the earth and it doesn't allow us to fly around like Superman, although how cool would that be? But what exactly is gravity? Well, gravity is a force of attraction. That's right. You know what a force is, a push or pull on an object. Well, gravity is a force. And that force of gravity is pulling on you right now, keeping you firmly planted on planet Earth. But who was it that came up with this idea of gravity in the first place? Well, he didn't invent it, but Isaac Newton really thought about gravity. And he was the one who really developed the idea that it was a force of attraction. So why don't we do something interesting now? And why don't we send Inertia Man back in time to the 17th century when Sir Isaac Newton was alive, and let's check out how did Newton come up with this idea of gravity.
Why are objects attracted to one another?
Now that's a good question. And it was Sir Isaac Newton who developed the answer to that question. What he found was this force of attraction between objects that we call gravity is a result of mass. Mass is the amount of matter in an object. The more massive something is, the more matter it has. The older I get, the more massive I become as I gain weight. But weight is a topic for another day. So mass, the amount of matter in an object. Now, larger masses have a greater gravitational force. Let me explain. You may recognize this as a model of the Earth and the Sun. And around the Earth orbits the Moon. Now, why is it that the Moon goes around the Earth and the Earth goes around the Sun? Well, the reason for that partly is mass. The Sun has the largest mass, and so the Earth orbits the Sun. The Earth is more massive than the Moon, which is why the Moon orbits the Earth. The Earth is much more massive than you and I, which is why we are stuck on planet Earth and we just can't fly off whenever we want to.
Is there gravity in space?
Another good question. In fact, I would imagine most people, if asked that question, would probably answer the question wrong. What do you think? Is there gravity in space? Think about it for a moment. Sir Isaac Newton suggested an answer. And later on, we're going to be talking about someone by the name of Albert Einstein who came up with an even better answer. But the simple answer to that question is yes. Is that what you said? Or did you say no? Most people say no. Outer space, there's nothing out there, right? There's no gravity. Well, gravity exists everywhere there is mass. And in the universe, there's a lot of mass.
Can we ever be weightless?
I'm so glad you asked that question. The reason why most people answer that previous question wrong is because they think, well, wait a minute, what about the astronauts that float in space? It's like they're not being acted upon by any gravitational force. What's up with that? Well, check it out. There is something that we do call zero G. But what exactly does that mean? Well, experiencing zero G is describing a condition we call being weightless. It doesn't mean you don't have any mass, but it means something else. Let me ask you, have you ever seen astronauts floating around in space in the space station and wonder, well, how can they fly like that? That's pretty cool. They are experiencing zero G, or a condition of weightlessness which is caused by, get a load of this, free falling. They are falling down all the time relative to the Earth as they orbit it, and that's what makes them weightless and able to float around. Now, you don't believe me? Well, I'm going to show you a clip here of some special needs individuals who had a fantastic opportunity to experience zero G. And in this experience, they all take a ride in an airplane called the Vomit Comet. And you'll see why in a moment. Not that we'll see any vomit, but you'll see. And the European Space Agency, the ESA, is the one who sponsored this Make-A-Wish Foundation project for these individuals to experience weightlessness, just like the astronauts floating in space. So as you watch this, I want you to ask yourself, would you ever want that opportunity to be weightless? For this activity, I would like you to lay your head down for about a minute. And while your head is laying down for about a minute, I want you just to relax. You can be laying down completely. That will make it work even better. So if you're laying down on the floor, that would be fantastic. But as you're doing this for about a minute, I want you to think about what's happening inside your body. All of your blood is flowing to all parts of your body, including your head right now, and gravity is acting equally on all parts of your body. Now, after about a minute, I'm going to ask you to lift your head up quickly to see what happens. Are you ready?
I didn't hear you. Are you ready? All right, here we go. 3, 2, 1. Lift your head up. Whoa, I feel a little bit dizzy. Did you feel a little bit dizzy at all? If you did, it might be because when you lifted your head up, gravity was pulling all of the blood out of your head back to the rest of your body. And when that happens, it takes your body a little while to get used to gravity again. The astronauts that come back from space also have to get used to gravity again, because when they are orbiting around in space, gravity isn't pulling their blood down like it is normally when we're here on Earth, and it can make them feel a little lightheaded when they come back to planet Earth. So perhaps you can try this little activity again with someone else in your home. Have them lay down for about a minute, and have them stand up real quick, and they too can experience the pull of gravity on the blood inside your body. I have a model of the solar system here. I want you to look at the solar system. Notice all of these smaller spheres are planets that go around this larger, more massive object in the center. Do you know what it is? What is in the center of our solar system? And why is it in the middle of the solar system? Think about that. Have we ever gone to the moon? Well, the answer to that question is yes, but we haven't been there in a long, long time. Between the years 1969 and 1972, NASA had a mission called the Apollo program. And during those years, 12 American men, set foot on the moon and walked around on the moon. No one else has ever been to the moon. Only 12 American men. And the last time we were there was 1972. And I'm actually old enough to remember that last moon voyage. And unfortunately, I think it's a bit sad that we haven't been there in so long. However, you have something to look forward to, because NASA has recently announced that in the year 2024, that's only 4 years from now, there's going to be a return to the moon. We are planning to send America's first woman, forget about America's first, our planet's first woman, to go to the moon by 2024 in a project called the Artemis Project. So, I hope you study hard in science, keep on asking questions, and maybe if you're interested, maybe you too could become a fellow moon walker. Now, because it was so significant, I just want to mention the very first moon landing. It was Apollo 11, the very first time that human beings landed on the moon. Apollo 11 was manned by Neil Armstrong and Buzz Aldrin. The first one to come out of the spaceship to walk around on the moon was Neil Armstrong, and the second one was Buzz Aldrin. Now, I just got done reading a great book, No Dream is Too High, written by Buzz Aldrin. And did you know that Buzz Aldrin was born and raised in New Jersey? Yes, he's one of us, folks. The first
mission to land successfully on the moon was Buzz Aldrin. And I almost said Mars because Buzz Aldrin is crazy about Mars missions. He has been pushing for years to get human beings to land on Mars. Now, he's getting pretty old himself, but the groundwork that he has laid and the research that he has done may take you there one day. But check out these clips right now of the very first moon landing. And the name of that ship that landed on the moon was the Eagle. So watch the Eagle landing. Is there gravity on the moon? How do you move on the moon? Well, that's actually a tricky question. A better question might be to ask is instead of saying, is there gravity on the moon, say rather, does the moon have gravity? Because remember what gravity is. Gravity is a force of attraction that objects with mass possess. So gravity isn't like an object that you can place somewhere. It's a property of matter that is possessed simply by having mass. So, in answer to the question, the intended question, is there gravity on the moon? We can definitely say that the moon has gravity. The moon has gravity because the moon is made of matter, and the amount of matter something is made of is called its mass. So when the astronauts went to the moon, they weren't able to fly around. They got around in their unique ways while on the ground or the surface of the moon. But it was different than here on Earth. And the reason for that is because the moon is smaller than the Earth. And because the moon is smaller than the Earth, it has less mass. Look at the model. You can see that the moon is smaller than the Earth. So what we experience on Earth when we're walking around in what's called 1g, or 1 gravity compared to the Earth, when you go to a smaller body like the moon, since it has less mass, it's not attracting us as much. In fact, on the moon, gravity is 1/6 that of Earth's. So check this out. If you could jump 1 foot off the ground on Earth, on the moon, you could jump 6 feet off the surface. Imagine the Olympics on the moon, being able to jump and run and do things that you can't normally do here on Earth.
Alright, you do have to be rather careful to keep track of where your center of mass is. Sometimes it takes about 2 or 3 paces to make sure that you've got your feet underneath you. And about 2 or 3 or maybe 4 easy paces can bring you to a fairly smooth stop. Direction. Like a football player, you just have to put out to the side, cut a little bit. So-called kangaroo hop does work, but it seems your forward stability is not quite as good as it is in the conventional, more conventional, one foot after another.
Why doesn't the moon just fly away from the Earth? Now that's a very good question. To try to answer that question, we have to think of a couple of words that we've learned already today. Basically, the answer has to do with those two words, inertia and gravity. Remember, inertia. Do you remember what inertia means? Lazy, that's right. And gravity. What does gravity require? What is involved with gravity? Gravity is related to mass. So inertia and gravity. Well, Sir Isaac Newton came up with this idea that led to a description of how the planets orbit around the sun and why the moon orbits around the Earth and doesn't just fly away. Let me try and demonstrate for you. Here I have a ball that is connected to a string. And this ball has a certain mass. And I'm going to swing it around. Now, let's pretend that my head is the Earth and this ball is the moon. Well, why isn't it just flying off in the room? Why is it orbiting my head? Well, as you can probably see, there are a couple of reasons. Number one, it's attached to this string that I'm holding on to. Well, this string that I have represents gravity. The string is the gravitational force that's holding this rotating, orbiting object around my head. But the other thing is that it has inertia. Remember inertia? Inertia, laziness. This ball just wants to keep on doing what it's doing. It's happy to just keep on spinning around and around and around my head. These two things working together is what causes objects to stay in orbit. Now, what do you suppose would happen if one of these things stopped? Well, let's take gravity. If gravity somehow were to magically disappear, which don't worry, it's not going to in real life, but in our little model it could. If gravity were to disappear, then I would stop holding on to this string. What do you think will happen if I let go of the string? What do you think will happen if gravity would cease to exist? Are you ready? I'll give it a 3, 2, 1 countdown. Count with me. 3, 2, 1. Did you enjoy watching those videos of astronauts moving around on the moon? I know I did. Now, the astronauts, when they were up there on the surface of the moon, they had to deal with a different level of gravity than we do here on Earth. And they also had spacesuits on that were hundreds of pounds here on Earth. Not quite as heavy on the moon. But they found different ways to move around. One way was skipping. Another way was jumping. And the third way, my favorite, the kangaroo hop. I'd like you to get up in a safe place in your home or outside, and I'd like you to try those 3 ways of moving here on Earth. But pretend that you're on the moon. See which one is the easiest for you. I have a book here all about space. And I have a question for you. Do you know what the major feature of the universe is? Let's open the book and find out. Do you know what these are images of? If you said galaxies, you're right. Nice job. Galaxies are a major feature of the universe. Let's find out what holds them together. Who was Albert Einstein? I think most people would agree that Albert Einstein was probably one of, if not the greatest minds of the 20th century. Albert Einstein was a brilliant scientist, but a wonderful humanitarian as well. So let me tell you a little bit about Albert Einstein and how he ties into our topic with gravity. Albert Einstein was a Jewish German scientist. So he came to the United States and actually settled right here in the state of New Jersey. Now, we're not going to get into this equation today, but it stands for energy, mass, and the speed of light. And what he did throughout his life was give us a greater understanding of how the universe works. So Albert Einstein, brilliant individual, great scientist, and really a wonderful human being. What did Einstein say about gravity? Now that's a fascinating question, and one that's really difficult to explain and give a really good answer to. In fact, scientists are still trying to figure it out completely. But basically what Einstein said is that gravity changes the shape of space. Gravity curves space. Now, to understand that, let me try and show you a little demonstration. I have a bowl here that is see-through. I've got plastic wrap on the top. The surface is very flat. Think of this flat surface as the shape of space. Now, if I take a small object like a little marble, it has a very low mass. I can take this marble and roll it through space. Whee! Whee! It rolls pretty much in a straight line because, well, in this case, space is flat. But what Einstein said is that objects with mass do something to the shape of space. So let me demonstrate with a marble that has a little more mass. Notice what happens when I place this object into space. The mass of this object is pushing down on the plastic wrap. It is changing the shape of space, which means this. If we take that smaller marble that once went in a straight line when there was no other mass there, watch what happens when I roll the marble now. Ooh! It goes right into the center. Oh, goodness, it doesn't come over to you anymore. In fact, it almost goes into orbit right around this larger object. Whee! Whee! Whoa! That is how Einstein explained how objects stay in orbit around more massive objects. It's the change in the shape of space. Is there gravity in space? That is a good question. As long as there is matter in the universe, then there are objects that have mass. And as long as there are objects that have mass, they are changing the shape of space itself. So is there gravity in outer space? Well, yes, there has to be. Gravity is the glue that holds the entire universe together. And now it's time for our final activity together. We are going to be constructing a spiral galaxy that you can play with. Yes, when we're finished, it's going to look like this. A spiral galaxy in the palm of your hand. When you move it back and forth and travel around through space, the space of your room, the space of your house, the space of your yard, wherever it might be, it's going to be able to spin around and around just like a real spiral galaxy. So how do we make one? Let me show you how. All you need is a paper plate, a pencil, scissors, and a push pin or a tack. And if you have a helper, that would be great too. So, if you have a paper plate that's completely flat, you can bypass this first step. But if your plate looks like mine and it's got a big groove in it like this, a big bulge around the edges, then take a pair of scissors and cut that bulge or that curve off of the edge of your plate. Because what you want to end up with is a nice flat disc. In fact, there are some galaxies in the universe that are just that, flat disks. And some galaxies are more like blobs, and then there are some galaxies that are spiral galaxies, like our own Milky Way galaxy. So we're going to make a spiral galaxy like our own Milky Way. So here's a flat disk. Now comes the next part. Using your scissors, you're going to make a number of cuts toward the center, but not all the way to the center of your disc. This is part of the experiment. You can change how many cuts you want to make, but I'm going to start with 4. So 1 from either side of your disc, and I'll rotate it and do the same thing from this side. So now I have 4 slits cut through the disc. Next part. Helper might be helpful here too. My Einstein duck is going to assist me with this. We're going to take each of these little triangles that we've made, and we're going to fold 1/2 of it upwards. And we're going to work our way around, following the same pattern, making sure that each of those is folded upwards. You can also fold the opposite side down if you want, and work your way around as well. And now the final part. Take your push pin and very carefully put it through the center of your galaxy. Just like gravity holds galaxies together in real life, your push pin will hold your spiral galaxy together. Put it into the end of an eraser on a pencil. Make sure it can freely spin around, and you're done with your toy. Now you can move your spiral galaxy around the room, around your house. You can have lots of fun for the rest of the day, maybe even the rest of the week, playing with your spiral galaxy while you remember that gravity is the glue that holds the universe together. Well, I'd like to thank you for joining us here today. I hope you've enjoyed the lesson on gravity today. I hope you had a little bit of fun. Perhaps you can do some of the activities later on. And I hope you continue to watch New Jersey Public Television as you learn more. Even though you might not be in school, keep on learning, stay curious. But before we leave, I just have 2 questions for you at home. First question is this.
What holds the universe together?
Did you answer gravity? Because that's the right answer. Good job. If you answered gravity, then I consider today's lesson successful. But I have one more question for you, and I want you to think about this very carefully.
Are you a scientist?
I hope you answered yes. Remember, if you are curious, you like to ask questions, and you like to find answers, then you are a scientist. So thank you again for joining me, fellow scientists, and have a great day.